Swayam Prabha. Digital India. Educated India.
So welcome back. So in this next talk, I thought I will talk about yet another application of, equilibrium concept in more contemporary field, namely deep learning. I'm sure all of you would have heard this term deep learning at least, right? It's becoming so deep these days in our life that I doubt if anybody would not have heard term deep learning. Whether they know or not, that's a different issue. But I thought I'll say something about this because there is some, intriguing connection between game theory and some of the recent advancements in deep learning. So there is one model which was proposed in recent time called generative adversarial network GAN, and that has become phenomenally popular because it has given rise to many fields of research and given rise to many fantastic technologies, right? And at the core of it lies is some equilibrium concepts which are very similar to Nash equilibrium, which I was talking in the previous talk. So I thought that it's a very nice topic to talk in this forum, right? On one hand we are learning about game theory, on other hand we are talking about applications, and this happens to be the most contemporary field actually. So why not talk about that, right? Little different than morning talk actually. I'm switching the gears now and we'll come back to the crowdsourcing maybe after lunch again, right? Okay, so let's start with this. This is called as adversarial approaches in deep learning, and this term called adversarial has become quote unquote very popular in deep learning arena these days. A large number of paper titles, if you look at in top conferences like ICML, ICLR, NIPS and all that, you will find a large number of paper titles having adversarial word actually. What is so adversarial? So it all started with the GAN, okay? Phenomenal piece of work by a gentleman called Ann Goodfellow. He was a student of Professor Yoshua Bengio, okay? One of the Turing Award winner of this year among three, right? So he proposed this originally, this concept, and then it is so popular in less than 5 years time it acquired 10,000 citations, that single paper. You can see that, the profoundness of the idea actually, okay? Okay, so this is the roadmap for this topic of the talk. So I divided logically this talk into two parts. Initial some part will be related to more economics, econ part I call it, or maybe more related to game theory and economics in general, because I need certain fundamentals and concept for all of you to know before I can jump to the GAN, right? And the second part of this talk will be more CS related, more deep learning related, where we will be talking about GAN. So the first part, what we will be talking the ideas such as what is min-max solution, what is max-min solution, what is saddle points, then very popular result called von Neumann's theorem, okay? And in the second part, then we will be talking about what is generative adversarial networks, GAN, so to say in short, the gap between theory and practice, and if time permits, I will also talk about one interesting problem called domain adaptation problem, very important problem in deep learning that also has interesting traces of some of these ideas, all right? Okay, so let's start with this econ part first, and we will go about understanding what is max-min, min-max, saddle point, and what is the difference between all of them. Let's start with min-max problem. So how many of you have heard at least term optimization? I assume some of you know what is optimization, what is minimization, what is maximization, all right? So let's start this something called min-max problem, okay? Min-maximization, what does it mean actually? So a min-max optimization problem is given in the following manner. Let's say there is a function called f x comma y. It is in two variables x and y. X itself could be a multidimensional variable. X itself could be a d-dimensional variable, okay? But as a short notation I am writing it as a x, which is the set of unknowns. Y is also another set of unknowns, right? Now the problem is the following. You want to minimize this function with respect to x, and you also want to maximize the function with respect to y. Okay, what does it mean? Let's try to understand. It's a very, the way it is written, it may be a little confusing. What do you mean by minimizing this and maximizing that? So we'll slowly unfold it, mystery, and then try to understand what does it mean actually, okay? and you have to be really careful in because in next 15 minutes the kind of concept which I am going to talk about, it's very easy for you to get confused. So please pay a proper attention to this next 15-minute slides, okay? Okay, so what is f? So f is a function which goes from, let's say, some space x and y, where x is some Euclidean space Rm, okay? Y is some Euclidean space Rn. It could be even m and n has no connection. They could be same, they could be different, they both could be one, doesn't matter actually. So these are some vectors. It could be real number also. Fine? Okay, so then what? So a point x star comma y star is said to be a min-max point if following happens. Okay? So there is a region called x and y, right? There is a set called x and y over which you have defined a function fx comma y. Now in that region, a special point called x superstar and y superstar is called as a min-max point if this point satisfies the following condition. What are those conditions? So first of all, x star should be the minimizer of another function called phi of x, where what is phi of x? So phi of x is nothing but, you know, I have taken, let's say you claim the first part of this expression. So this first part which is called max y fx comma y, what does it mean? This definition of this min-max problem means first you clamp at the value of x. You take any value of x, clamp the function at that x. Don't move x. Over the all possible values of y, you maximize the function. So obviously that quantity will be function of x itself, what you clamped at, right? Let's call that function as phi of x actually. Now what you want to do, you want to further minimize this function with respect to x. Make sense? So this x star is such a point which is the minimizer of this function called phi of x, where phi of x itself is what? Phi of x for any x is nothing but after I claim the value of x in this function, it is a maximizer over y. Making sense? Okay. Now what is y star then? So if you know the function phi x, you can find x star. After having found x star, we will find y star. What is then y star? Now I will clamp x at x star in this function phi of x, right? While defining, so this is essentially phi of x star. So I know that phi of x is what? After clamping at x, I am maximizing with respect to y. So if I clamp x2 at value x star, then whichever y maximizes that function, that y is called as y star. Is it clear now? 2 points to note here. Ordering is very important. Min-max is not same as max-min. Point number 1. The ordering is very important. I have written min and also I am minimizing over what? That's also very important. There are two sets of variable x and y. Over one I am minimizing, over one I am maximizing. Symbol doesn't matter. You can call x as y, y is x, doesn't matter. You can swap them. It's just a notation. That's not important. But whatever you call it as a min, whichever set of variable you are calling as a min, that is coming first. And whichever set of variable I am doing max, that is coming next. That is the hallmark of this problem, and that is why we call it as a min-max problem. Later on we will also see there is something called max-min problem, where what I will do, I will swap the order. I will keep the variable same, I will still maximize with respect to y and still minimize with respect to x, but I will change the order. That problem is called max-min problem, and that's a very different problem. Is it clear? Will you remember, min-max is not same as max-min. Okay? Even though if I do the minimization over same set of variable and maximization still over the same set of variable, but whether I am doing minimization followed by maximization or maximization followed by minimization, these are entirely two different things. In fact, they could be drastically different things actually, and you will see that. If any doubt, please let me know. Is this definition clear or not? What is x star and y star? So x star is nothing but minimizer of function phi of x, where phi x itself is obtained in what manner? By clamping at x and then maximizing over y, right? And how you get the y star? In order to get the y star, you have to first find x star. You cannot get y star directly, right? You have to first find x star. Having found x star, you clamp this function f at x star and then find the maximizer of it, and that maximizer is called as y star. So far so good. Let's take few examples, okay, to make things more clear. Suppose my function is over finite domain. What do I mean by finite domain? X can take only finitely many value and y can take only finitely many value. So I have arranged this table. So suppose x take only m possible value, x1, x2, xm, and y can take n different values. Suppose my x and y are just few points actually, my function is defined over few points, okay, and y can take y1, y2, yn, and in any of this cell, let's say ijth cell, f of xi comma yj means the function evaluated at xi and yj, I put this value here. So this table is clear, this construction is clear. This is an example function f, which is defined over two variables x and y, where x can take only finitely many values, y can take only finitely many values. It is just an example. In general, x can take any value. X could be a real number, x could be a two-dimensional vector, x could be a d-dimensional vector. Same y could be a real number, y could be d-dimensional vector, anything can happen. This is just for illustration's sake, I have taken x in some scenario where x can take only finite value, y can take only finite value, and for any I comma jth pair, the function value we will write down in this cell. It will be some number. It will be some real number. So think of that this table is filled with numbers. That's all. It's a m cross n table filled with numbers. So far so good. Now let's go back to our min-max problem. When we said that I want to find min-max value of this function, what did we say? First step is to find the function phi of x. So which means you clamp the value of x. What do you mean by clamping? Here clamping value of x means take a row. Taking a row means clamping the value of x, right? And then if I take a max in the row, that will give me what? Phi of x. Make sense? Are you with me? So let us say I write another column which I call phi column. So what will this value will be? If I take this row max, this value will give me what? Phi of x1. Similarly, this row max if I take and write it that value here, that will give me phi of x2. Like that I will get phi of xm. With me? Okay. You remember in min-max problem, we were first clamping the x and then taking the row max. Now I have to take min over x, min over phi x. So what I have to do now? Minimum of which values? Minimum of this column. Make sense? So let's take the minimum of this column min. If I take this column min, whatever number I get here, it will be some number, right? This number is called min-max value of this function. Is example clear? How you compute the min-max value? This is just an example, but if this, imagine now if x and y are real spaces, they are d-dimensional vector, how will you compute? That's a big deal actually, we'll come to that. They are not as simple as, doing this hand calculation here. A very simplistic scenario, but idea is same, concept is same. Fine with me? Okay, now which point will be x star and y star point? Let's try to find out. See, this is the value. So there are two things. One is called min-max value, another is called min-max point. So this number will be min-max value, but the x star and y star, I have to also give you a point. What will be that point? So how will you find? First you have to find the x star. Which point will be x star? When you are taking this column min. So some cell will be min value, right? Whatever cell is the minimum value, that corresponding xi is x star. Make sense? For same cell, now when you are getting this phi of x, you are getting by taking row max. So this row max will be attending at some point, right? In this row, in some cell that max value will be occurring. That corresponding column, you go to the corresponding column and find that y, that will be your y star. Is it clear? So the difference between min-max value and min-max point is clear. Can I move? If any doubt, please feel free to ask. Okay, let's take one interesting example. So this was a discrete setting. Let's take a continuous setting. Okay. Here is a function called f of x comma y equal to x square minus y square. And this is the plot. Okay. So this is the function which is over the continuous values. X is real number, y is a real number, but I have plotted this function only in the interval -1 to +1 and y also -1 to +1. So there are infinitely many points. I cannot plot it as a table now, right? Because they have infinitely many points. So this z axis here, that is nothing but value of this quantity, x square minus y square. And this is how it will look like, this surface. This is popularly known as, what it is known? Saddle. This is called saddle function. Why saddle? Like in horse, when somebody sits down, you would have seen the seat on which you sit on horse. So there are, if human being sits on the horse, there will be two legs, right? So one leg this side, one leg this side. This is typically called saddle. So this is the plot of a saddle function. Let's try to understand for this function what is the min-max point. In order to do the min-max point, what I have to do? Clamp the value of x and then find over this value of y what is the max. So how will I do? I'll cut this function. So I take a knife and cut it. This surface along this x-axis, right? Along this axis. Take at any value of x, like you cut the apple, right? Like that I will cut it and I look at the edge actually. That will give me a one-dimensional function now along the axis of y. If I cut this surface by knife, let us say, where my knife will be parallel to this axis y, I will put that knife at some x actually, right? Think of this is like a cake actually, and you are cutting a cake, but your knife has to be run in parallel to axis y, and where you put the knife, you will cut the cake, and then you look at the edge. That edge will be function over y, and you find the max value. That will be your phi of x. Like that you keep doing for different x. So if I plot that function, how will that look like? This is how it will look like, okay? You can try at home actually. If you clamp a value of x for this function, and then you try to find the maximum value of y, or the value of the function, what is the maximum possible value function can get for that x, and you plot this value of maximum value of the function for the fixed value of x, this is how the plot comes, okay? It's very simple. So what will you do? Look at this function. If x is constant, this function is in one variable y square minus y square, because x square is constant now. And what will be the maximum value? In order to find the max, what will you do? You will take first order derivative actually and set it to 0. So what will be that value? Minus 2y, right? And then the second derivative is negative. So it's a point of maxima, correct? So at y equal to 0, the point of maxima will occur. For any value of x, the point of maxima will occur at y equal to 0. So then if you plug that back actually, for any clamped value of x, the maxima will occur at y equal to 0. And you plug that back, then phi of x is x square. And that's what this plot is, x square. Clear? Okay. Now let's try to find out its min-max value and min-max point. So what is its min-max value? So look at this. The minimum point occur of phi of x, the minimum value is occurring at x equal to 0. So which means our x star is 0 for sure. Now what is y star? Anyway, we saw that it's y is 0 for any x. So y equal to 0 is a y star and x equal to 0 is x star. So this 0, 0 is your min-max point. And if you look at it, this function, this 0, 0 occurs somewhere here. This point is called min-max point of this saddle function. Is everybody with me? And what is the min-max value? The min-max value is the value of the function at that point. And this is 0 in this case actually, because if you plug x 0, y equal to 0, this function value will be 0, right? So this is 0 value. So far so good. Any doubt, please ask me. Let's look at another interesting function where it is also in two variable, but this is called monkey saddle, okay? So why monkey saddle? Suppose if monkey were to ride on horse, right? So monkey has two legs and one tail. So the legs will be supported by these two sides and the tail will be supported by this side, okay? That's why they call it as a monkey saddle. It's like seat for monkey to sit on, okay? Interesting functions. So this is how the function looks like. This is called y cube minus 3yx square, and x and y is in the range of -1 and +1. Again, I have claimed the value of x and y in this range. It could be even infinite range also. You have to work out the calculation accordingly, right? So then what happens? Again, do the same calculation. In the interest of time, you believe me that if you do this, if you claim the value of x here, and again take the first order derivative, set it equal to 0, and you will get some value of y, plug that value y back actually, and you will get this function phi of x. So if you claim the value of x here and differentiate it with respect to y, you will get 3 times y square minus 3 x square. That is equal to 0, right? That's what you will get. So after that you solve this equation and then you will find at what optimal value. So then y will be equal to, I guess, plus minus x actually. And if you plug that value back, you will get this kind of a function, okay? Now where is the minimum of this function is occurring? So this is my phi of x function. Where is the minima is occurring? At minus 0.5 and the plus 0.5. These are the 2 points. So this function has 2 x star. Minus 0.5 is also x candidate x star. Plus 0.5 is also a candidate x star. Now what is y star, right? So suppose if you take this minus 0.5 as the candidate choice and then go here and hunt for the maximum, which is the maximum along this axis. And similarly, you can do for minus 0.5 and plus 0.5. So I am directly plotting for you, you will find these 4 points actually, okay? And these 4 points happens to be like this. See, plus minus 0.5 are the x star. The corresponding y star, there are again two choices, minus 0.5 and 1. You have to work it out, this calculation. So you will find that there are total 4 points, okay, which are min-max point. So this function has 4 min-max points and the value of this min-max value is 0.25. At each of these 4 points, the function value is 0.25. If you can have multiple min-max point, but the value of the min-max points, function value at all the min-max point will always be same. It cannot be different, and that is called min-max value of the function. Is it clear? Okay. And remember that min-max value is not the maximum possible value of the function, neither it is minimum possible value of the function. For example, in this case, this 0.25 is not the maximum value of the function. There are some point where function value is much higher. Similarly, there may be some point where function value is even lower than this actually. So these are not the point of global maximum or global minimum. Neither they are the point of local minimum and local maximum. There are some peculiar points actually, okay? But they have very profound, interesting connections with something called, fixed points and the saddle points and the equilibrium points, which we will see in a minute actually, okay? And that's where theory starts becoming very interesting, okay? All right. Let's define its cousin called max-min, okay? So how does its cousin look like? Look at this. I have just swapped the order. It's very important to remember that function is same, but I have just swapped the order. Instead of doing min-max, I am doing max-min, okay? And the variable over which I am doing minimum and variable over which I am doing maximum, they are still the same. That I have not changed. Very important point actually, right? So I am still doing minimization over x. I am still doing maximization over y, but now I am first doing maximization, then followed by minimization, all right? Now, again the same setup continues. Now we define a point x lower star and y lower star to be the max-min point if the following thing happen. So like earlier we were saying that x star, now we will define y lower star first actually. So what is y lower star? So here you claim the value of x first, right? Let me just roll it down. So first let's look at this function psi y. Like earlier we looked at the function phi of x. Here we will define this function called psi of y. What is psi of y? If you claim the value of x, there we were claiming the value of, here you have to claim the value of y. Earlier you were claiming the value of x, right? Now I will claim the value of y because, so always we go from inside to outside actually, okay? The notation means that you have to first solve the inner problem and then outer problem. So when you go from inside to outside, you first fix the value of y, clamp to some value. After clamping, now y is constant, that is no more a part of the variable. So then I have to solve the minimization over only x, correct? Now if I solve this minimization over x, that function I call it as a phi of y because that will depend on what y I claimed at. Let's call that as psi of y. And then the leftover problem is to maximize over y actually. Make sense? Now, so then a point x lower star and y lower star is said to be the max-min point if the following happens, that y lower star should be the maximizer of this function, like earlier what x star was, right? And having found this y lower star, now you go and plug this y lower star back here and find the minimizer of this function, that is called as a x lower star. So it's just like mirror image, you can say, right? But they are not one and the same. They are in fact very, very different quantity. And that's where now things become very interesting. I'll show you. Okay. Now, okay, so just to continue on the same things, exactly same function I take, exactly same function, and now I want to compute the max-min. Earlier what were we doing? We were first taking row max, then column min. What we will do now? First we will take column min and then do the bottom row max. How we will do? So let's say, so earlier you remember I was writing phi here, now I am writing psi here at the row. So you take the column min, okay? So you claim the value of y, you take the column min, what you will get? You will get psi y1. Make sense? Again claim the value of y2, y3, yn, and you will keep on getting those corresponding psi y1, psi yn, right? Then because it's a max min, I have already taken min operation first because I come from inside to outside. Now I have to take the max. So max over all these numbers. If I do max over, which means row max, okay? So if you do that, whatever value you get here, this will be some number. This is called max min value, right? And which point will be your max min point? Of course, you first, so to find the max min point, you come from outside to inside actually. So wherever you did row max, you find the cell which is the maximizing cell, right? That point will be y star, y lower star. Now go to that column and find the row which was where your cell which was minimizing the column, that will be your x star. Fair enough? Any doubt? Okay. So this is called max min value and the max min point. Okay. Let's go back to our old friends again. These are another example in the continuous space, the saddle and the monkey saddle. And how do their min-max point you remember now, right, in the image. Where was min-max for this function? Here, right? And max min was some, here for this guy there were 4 points actually. Now what happens? Now look at this. Actually this is y, this somehow this is hidden. This x-axis is y, okay? So for any value of y, I am now clamping. So this is like a cake. This time you will cut the cake by keeping your knife parallel to the x-axis, okay? At different position of y you cut the cake. Whatever value of y you clamp, you cut the cake, look at the resulting edge of that cake and find the minimum value and plot that minimum value here. So this is a function of psi y with respect to y. And then I will find the max of this. So where is the max occurring here? At 0. So now my y lower star is 0, right? And if you have to find x lower star, what would you go? You clamp that y to be here and then see where the function gets minimized, right? That will be your x lower star. So in this case, it so happen that for this function, min-max and max-min point is same, min-max and max-min value is also same, namely 0. It just so happened, but need not happen in all the function. And that's where I am going to show you the monkey saddle. In monkey saddle, if you plot this function called y versus psi of y, it looks very different. Do you remember that how this function was looking there? It was looking like W kind of a shape there, right? And then we were finding the point of minimum and then going and finding corresponding point of maximum. Here it's a very weird shape actually. So here if you find the point of maximum, this is at y equal to 0, right? Now fix this, clamp this value to y equal to 0. Along this you have to find the point of minima. So this is how it happens. It has infinitely many point of max-min point. Every point sitting on this line is a max-min point, okay? The function value is constant. So as I told you, there could be infinitely many min-max point, infinitely many max-min point, but the value of the function at each of those min-max point and each of those max-min point respectively will be same. It cannot be different. So the function value at all these points is same. And what is that value? That is 0. Do you remember what was the min-max value of this function? 0.25. But here what is the value? 0. In this function, what was the value, min-max value? 0. What is the max-min value? Very good. So here is one example where min-max value is equal to max-min value. There is another example called monkey saddle where min-max value is greater than equal to max-min value, right? So this is the very first important result which I want to share with you, min-max versus max-min. If somebody gives you a function, you can always compute min-max and max-min. It could be even plus infinity and minus infinity. Max-min could be plus infinity, right? Sorry, min-max could be plus infinity and max-min could be minus infinity. But min-max value of any given function will always be greater than equal to max-min value. This is the fundamental result. It is equivalent to lim sup is greater than equal to lim inf. I don't know if some of you have taken linear algebra course, this real analysis course. It's a very basic result we teach actually in limit theorems, right? I mean, I could connect that easily with this, but this is the result actually, okay? So what am I trying? Let me summarize. Somebody gives you a function, no matter how weird that function looks like, always remember 2 points. No matter how the function looks like, once you have decided the set of variable over which you want to minimize, once you have decided the other set of remaining set of variable over which you will be maximizing, you first decide that. This is your choice, okay? Right? You decide one set of variable over which you will be minimizing, another set of variable over which you will be maximizing. Call the ones over which you are minimizing as X set, call the ones over which you will be maximizing as Y set. Now, first of all, always min-max value will exist, always max-min value will exist, and always min-max will be greater than or equal to max-min. It could be equal also, but need not be, okay? Very important result, and you can play around. In fact, you should convince, this is like simple matrix game. Put any number, this is a good homework exercise. You fill this matrix with any number, I give you this challenge. Take this matrix, M cross N matrix, you can give it to your friends, your small kids, brothers and sisters, and ask them this puzzle. You take this matrix of M cross N, fill any number of your choice, okay? First you take the row max and take the column min. On another hand, you take the column mins and then take the row max. You will find that this number is always greater than or equal to this number. Sometimes they need not be same. In fact, it's a bit counterintuitive. You get my point? First I am taking the maximum of all the rows and then taking their minimum. In another case, I am taking minimum of all the columns and then taking their maximum. Depends on what numbers you have put in. It is quite possible that this left side number is strictly greater than right side number. But it will never happen that this left side number is strictly less than right side number, will never happen. No matter which number you put. Don't you see this as a magic? I mean, if you look this theorem in this manner, it seems like a magic actually, right? No matter how you fill this thing, this trick will always work. Okay. So, which means what? F of x superstar y superstar, this is what we denote, this we call as a min-max value of the function, is always greater than or equal to max-min value of the function. It could even be minus infinity. And this could even be plus infinity. For example, here, if I put one cell's value as, let us say, in each of the row, I have one cell which is plus infinity. Then what will happen here? Everything will be plus infinity. Even if I take their minimum, it will be plus infinity. So it's possible that left hand side could be plus infinity. That's allowed actually, right? In extended real line sense actually. But let's not worry, for our purposes, I think that's okay. And then those who don't know what is lim-in, lim-inf and lim-sup, please ignore it safely. I'm not going to use that. But those who are aware what is lim-sup and lim-inf, this connects back to your standard results in linear algebra. Alright, let's go to another distinct cousin called global saddle point. Global is very important word here. There is something called global saddle point. This is also known as Nash equilibrium. Okay? What is global saddle point? Nash equilibrium of two-player game, by the way. Not n-player game, okay? So maybe in one of the future talk, probably they will introduce Nash equilibrium in n-player game. But for this purpose, let's assume just there are two players and what is Nash equilibrium, okay? And that to zero-sum game for now. Okay, so I am coming more from this function perspective actually, okay? In future talk, probably you may find people introducing, Nash equilibrium concept from game perspective, but you will see that, I mean, this is more abstract view what I am trying to give you actually. It's a more topological view and algebraic topological view actually, which may be more useful for you actually, okay. So a point, suppose again I have same function, somebody gave me a function f which is in the space of x comma y, okay. Now a point xs comma ys is said to be global saddle point if what happens, okay. If this happens, this equation is very different. So what am I saying? So suppose there is a function which is defined over two-dimensional space x and y. In that space, I find one peculiar point called xs and ys. And that point I call as a global saddle point if the following thing happen. If I claim the function at y, if I claim the y at ys, if I claim the value of y at ys, and then if I try to find the value, minimum value of the function across x, because along x we are minimizing, right, throughout the discussion. So if you claim the value of y to ys, then the minimizer of the function in x will be at xs. Similarly, look at this right side equation, this second part of the inequality. First, don't worry about last part. Look at the second term and the third term. What have I done? I have claimed the y at the y. I am holding y fixed at ys, right? I fixed the y to ys. And then, what does this inequality says? It is saying that for all x comma y, this inequality should hold. Which means what? If I held y to be fixed at ys, then no matter which x I plug in, this function value is going to stay above the value of the function at f(xs, ys), which means what? Having fixed y at ys, xs is its minimizer, right? Now look at the other part, the first term and the second term. What have I done in the first term and the second term? I have claimed the value of x at xs. I am holding x fixed at xs. Okay, this x is held fixed at xs. Now I am letting y vary. Y can be any valid value. Now if I let y to be any valid value of y, as long as x is fixed, then what this inequality says, the function value always stay below the function's value at xs, ys, which means xs is the minimizer if you clamp at ys, and ys is a maximizer if you clamp at xs. Now you may be a little confused, sir, how it, I mean, it seems very, you can smell that it's very similar to min-max kind of a flavor, right? What is the difference? You have to think carefully. I mean, this is where I told you, warn you in the beginning, that these things are so subtle, you may get confused actually. I don't know how many of you are not confused. I'll be very happy if you are not confused. But those people who are confused, I'll also be happy because then I have something to teach you actually, okay? So I don't know how many of you are finding that I'm lost now, sir, after seeing this third cousin actually. Till second cousin it was okay, but this third cousin is confusing hell out of me actually, right? So let's compare them. Let's compare these two definitions, okay? So let's first look at this definition. What it is saying? So xs is the argmin of x, this function, when clamping y at ys, right? And ys is the argmax of the function while clamping x at xs. Let's go back to our compare with min-max definition. How it differs from min-max? In min-max, what were we doing? Same x star, we were taking the argmin of phi of x actually. Where phi of x was what? Phi of x was not some f of x comma y where y is held fixed at some constant value. You get my point? Phi of x was a very different function. You were clamping x at different points and then maximizing over y, and that's how you were getting the phi of x. And then you were minimizing over phi of x. Whereas here, in some sense you can think of that, this function is what? Here you are clamping the y, and your analogous to phi of x is this function f where you clamp the value of y. And this resulting function, if you want, you can view it phi of x, but this is not phi of x actually. Do you see the difference? Again, let me repeat. Phi of x function, how did we obtain the phi of x function? I think this definition is given here. Phi of x function we were obtaining by clamping the value of x and then maximizing over y. That is how I got the phi of x. And then now I am performing the minimization. Whereas here, what is happening? Here, I am not doing any of this x clamping business, okay? What am I doing? Instead, I am doing clamping y. I am clamping y at y star, and then the moment I clamp y at y star in the original function, the resulting function is now function in x actually. You get my point? Here also I got a function in one variable. What I was doing, I was clamping the value of x, maximizing over y. That's how I obtained another function which was function in x. But here what am I doing? In the original function itself, I am clamping the value of y, and then the resulting function is also a function in x. But these two are very different functions. Think about it, they are not one and the same function. So I am, while getting the x component in this third cousin, the x component of this third cousin is still some minimization problem, solving some minimization problem over function which is over the x, but these two are very different functions. And that's where I found in my experience most of the students get confused. Whenever we teach, you know, this two-player zero-sum game, the min-max point, max-min point, saddle point and all, utter confusion actually, okay? So I took this liberty to start from other way around, give you first definition of min-max point, max-min point, saddle point, and then first convince you that these three are three different points, three different notions. Clear? Alright, if this is clear, then this is also called as a Nash equilibrium of two-player game, okay? Think of that there are two players, player x and player y. Player x controls the variable x, player y controls the variable y, okay? And f of x comma y is, let's say, utility of one of the player. The other player's utility is minus of that actually, okay? That's why it's called zero-sum game. And that's where the von Neumann's theorem I'll show immediately. So what happens is when you do the min-max operation, so one of the players solves a min-max problem. Which player solves the min-max problem? See here, X player is minimizing and Y player is maximizing actually. So in some sense, what the player Y thinks is that, you know, the so suppose if F is the reward for let's say X player, suppose if F is the reward for the X player actually, right? Then what will happen? So if it is reward for the X player, then I'm just thinking whether it will be X player will be solving min-max problem or max-min problem. One of the player will be solving min-max problem, another player will be solving max-min problem, okay? So if F is the reward of X player, then I guess, right, yeah, so if no, suppose F is the reward for the Y player actually. Suppose F is the reward for the Y player, okay? So the X player's reward will be what? Minus of F actually, correct? So then what X player thinks is that whatever decision X I take, suppose I am an X player actually, I take some choice of variable X, I decide what should be the value of X. Whatever value of X I take, my opponent, who is the Y player, he or she will try to maximize their reward, suppose. So they will take some value of Y. Suppose there are two set of variable X and Y, and we are the two player. I decide what should be the value of X variables. You decide what should be the value of Y variable. These are called strategies in two-player game actually, okay? Having we both decided our values for X variables and Y variable, let's say reward for the player Y is F of XY and reward for me is just minus F of XY actually. It's like zero sum. So his gain is my loss, my gain is his loss. So typically then in Nash equilibrium of these two player zero sum game, what happens is this: if I am the X player, now I need to think what value at X I should fix, because I have no control what value he will fix actually. So how I think? I think in the following manner. I will do this deliberation in my mind that suppose if I take some value of X, now whatever value of X I fix, my opponent is obviously going to fix a value of Y which will be the maximum beneficial for him or her. So which value of Y they will choose? They will choose the value of Y which maximizes their reward, no matter which X I choose, right? So this will be the reward of my opponent. If I take X as my action, my player will take an action Y such that F of XY is their reward. If X or Y is their reward, then my reward will be minus F of XY. Now what I need to do? I need to maximize my reward. F of X minus F of XY I need to maximize, which is same as I have to minimize F of XY. You get my point? Is it clear? If I take a action X, I know that my opponent is going to take a action Y in such a way he will be solving this problem. If Y is my opponent player, Y will be solving this optimization problem and take the action accordingly. And if he has taken this action, then his reward will be F of X comma Y and my reward will be minus F of X comma Y. Correct? So now my dilemma is which X should I take? So obviously if my reward is minus X comma Y, minus F of X comma Y, in some sense minus phi of X, let us say, then I should try to take an X which maximizes minus phi of X, which is same as X which minimizes phi of X. And that's why I'll be solving this problem actually. So this optimization problem is essentially, you know, the X player will be solving this problem and the Y player will be solving just max-min problem, okay? But these are not the Nash equilibrium, okay? So that's where if you take any 2% zero-sum game, it may not have a pure strategy Nash equilibrium, okay? But it always has a mixed strategy Nash equilibrium, and that's where this von Neumann's theorem comes. So Nash equilibrium is this point. In game you always look for this point. So you are interested when the min-max point and max-min point, they collapse and becomes equal to the saddle point. That's your interest actually. Let's try to see that. So now try to understand. Before I get into, let me go back to our favorite example of this finite domain. In this finite domain we saw how the min-max, max-min points are calculated. How the saddle point is calculated, let me tell you. Exactly same setup. So these two calculations we have already seen earlier, min-max point and max-min point. We have also seen this result. Now somebody gives me same function. Now which point will be a saddle point? So a cell, this point, this cell will be called as a saddle point, or this X and Y pair will be called as a saddle point or global saddle point or a Nash equilibrium if this value of this cell is at the same time maximum in its row and minimum in its column. That's all. Is it clear now? Let me repeat. The same matrix I have taken here. Now I am interested in finding a cell where the value of the cell is maximum in its row and minimum in its column. Does there exist a cell? There may not exist any cell, by the way. But if there exists any cell actually, then that is called the saddle point value, and this corresponding x comma y pair is called saddle point. It may not exist, right? Okay, so then there is a very interesting result. It says that saddle point exists if and only if your min-max value is equal to max-min value, and vice versa. Very interesting result actually. See, remember that now if there is a gap, right, between min-max and max-min, there is always a gap. There may be a gap. If there is no gap between left side and right side, which means that they are equal. May be equal, may not be equal. For example, in the normal saddle, we saw that this left side is equal to right side. But in monkey saddle, it was not the case actually, right? So if left side is equal to right side, then function also will have a saddle point. And ulta also is true. If function has a saddle point, then guaranteed that left side will be equal to right side. Which means what now? The monkey saddle, right, which we saw that function, does it have a saddle point? It cannot actually by this theorem. Which means what? In that monkey saddle, if you go back to that monkey saddle picture, I think I may have on next slide. Okay, I don't have, so let me just go back to the previous slide and convince you. If you look at this monkey saddle, oops. Yeah, look at this monkey saddle. So what it says, essentially there is no point which is, at the same time row min and column max, okay? Which means there is no point x which is at the same time minimum across its x direction and maximum across its y direction. No such point. That's what is the beauty of this result actually, and you can convince yourself, okay? Okay, so now what does it essentially mean? So just to summarize, any given function will always have a max-min point, min-max point. Min-max value is always greater than or equal to max-min value. Saddle point may exist, may not exist. Saddle point exists if and only if min-max value is equal to max-min value. Not only that, in that situation, the set of min-max point is equal to the set of max-min point is equal to the set of saddle points. That's another interesting result, okay? So for example, in that saddle point, that normal saddle, we saw that min-max point is same as max-min point. The value is also same, and the same point is also saddle point, and the saddle value is also the same. Now there is this another thing called local saddle point, okay? This is also called local Nash equilibrium. I mean, although it's a bit abuse of term, or this is called locally stable point. Some of in control theory people use some of these terms actually. So what is local saddle point? We saw that global saddle point. So suppose you have same function and it doesn't have any global saddle point, which is possible, right? For example, monkey saddle doesn't have a global saddle point, but it may have a local saddle point. What is the local saddle point? So the local saddle point says that a point xl comma yl is said to be a local saddle point if it is a saddle point in a small ball around it actually. So if I take the x point xl and yl point and put a small narrow region around it, like you define the local minima and global minima, right, actually. So what is a local minima of a function? A point is called local minima if it is a point of minimum in a small vicinity around it, right? If you take the large vicinity, it may not be point of minimum, but a small vicinity, it may be point of minimum, okay? So if there is a global saddle point, that will obviously imply the local saddle point. Every global saddle point is a local saddle point, but not other way around actually, okay? Now local saddle point need not be equal to min-max or max-min point. They could be different point actually, right? Because global saddle point will always be equal to min-max and max-min if they exist, right, with the previous theorem. But local saddle point may still exist even if the global saddle point don't exist, and in which case they may be completely different point than min-max and max-min point, okay? Now characterizing the local saddle point is relatively easier, and under some appropriate assumption on a function, a necessary condition can be given by this. So if your interest is to find local saddle point, it's very simple. What does it say? You find a point xl such that the gradient vanishes So this is called gradient function, right? This is called partial derivative of the function. Like you do the one variable function. How do you find the point of minima or maxima? You take first order derivative and set it to 0. Now for a higher order function which is of multiple variable, instead of first order you will take its gradient, right? It's like partial derivative across each dimension. So this is the symbol used for that. So when I write this inverted triangle x and this function, what does it mean? Y has been clamped at the value of xl, yl. Now it is only in function of x. Now I am taking its partial derivative with respect to all possible x directions, and then in that partial derivative I am now plugging in x equal to xl and set it to 0, right? So you have to find a point xl and yl where these two conditions are satisfied, that their partial derivatives are 0 and this Hessian is called their second order derivative, right? So just like in you would have seen, right, for maximization second order derivative should be negative, first order derivative should be positive. So here the analogous condition here are Hessian, these are the metrics actually, right? So positive and negative metric doesn't make sense, but there is this something called positive semi-definite matrix and negative semi-definite matrices you would have seen, right? They are analogous of real numbers being positive and negative at a very crude level actually. So then what you do, you take the Hessian of this function with respect to x, and in this case because you want to minimize in x, so the Hessian should be positive semi-definite. Because you want to maximize in y, the Hessian should be negative semi-definite. So these are just the necessary condition, they are not sufficient condition. Like what does it mean? If a point xl, yl, if it is a local saddle point, definitely it has to satisfy this condition. But if a point which satisfies these conditions need not be still a local saddle point. Fair enough? Okay, with all this theory, it's important to, bring, one of the legendary figure in mathematical sciences and computer science, namely von Neumann actually. I am sure many of you would have heard von Neumann architecture, right, while taking some initial courses in computer science. So here is the gentleman, and he had very influential paper, okay, way back in 1928. What he said is, so now the obvious question in our mind will be that, sir, how do I know that for which function min-max value will be equal to max-min value? Because then I know the saddle point will exist. Or in which function the gap will be there, in which functions gap will not be there. Is there a litmus test I can perform? You get my point? See, obviously now curiosity will be what? We said that, for example, monkey saddle, left side is not equal to right side, but normal saddle, left side is equal to right side. So what is so special about normal saddle and what is not so special about monkey saddle? Can I characterize that? And this is the question, of course not completely answered, but partly answered by this very, very influential result. And in fact 0%, two-player 0% zero-sum game is a very special case of this more general theorem actually. You won't find this general theorem in many of the game theory textbooks actually, right? So what it says is, if you have this some function f(x, y) which is in two variable, and let's say x and y are compact and convex set. I don't know how many of you can correlate this. I mean, even if you are switching off, that's fine actually. Some topological property of this x and y sets. So if they are compact and convex sets in some topological linear spaces, and let f(x, y) is a continuous in each variable holding other fixed. So f(x, y) is a function such that if I clamp one variable, in the remaining variable it is continuous. That is property number 1. Property number 2 is the x domain and the y domain, they are both compact and convex domain actually. They are convex sets and they are compact set. Compact means closed and bounded actually, okay. Then another property which it says is f(x, y) is quasi-convex. So don't worry about quasi, just convex actually. In x, what are convex function? I hope everybody know what is convex and concave function, right? So convex functions are look like cup and cap actually, right? So if f, and we know that we are minimizing in x and maximizing in y. So because we are minimizing in x, we are asking that function be convex in x for every value of y, and similarly it be concave in y for every value of x. Suppose if your function has this kind of a property, not all functions may have, but this itself would be quite a rich class actually, right? So von Neumann's theorem was that I cannot tell you all possible functions, but here is a rich class of functions. You just test, this is one of the litmus tests. You take a function and ask this question, is function continuous, right? In individually each variable holding the other fixed, is function convex in x, is function concave in y and blah blah. If all of these things are true, then you go home, you don't have to do anything. Just rest assured that min-max value of the function will be equal to max-min value, and therefore saddle point will exist. And therefore the set of saddle point will be equal to the set of min-max point, will be equal to the set of max-min point, and all three values will be equal. But where do I get such functions from? I mean, that's your problem dependent actually, right? Your application dependent. So for example, in two-player zero-sum game, what happens, we define this notion called mixed strategies. I think in future lecture probably you will get introduced to that. So there what happens is your x variable become the entire probability, simplex actually. So all possible probability distribution over x variable. So suppose each of the x variable is my choice, my decision choice I can make. Player 1, player x has n number of choice, x1, x2, xn, which one I take, right? And then I can take probabilistically, I can take a random distribution over these choices and then decide actually. Same thing y can do. In which case your space x is not the variables, that is the space of all possible probability distribution over x actually. And for y, this is again a space of all probability distribution over y. They are the compact and convex domains. And over that, if you take the expected reward, then those functions very easily you can verify that they satisfy all these conditions, and therefore by this von Neumann's theorem, the mixed strategy Nash equilibrium always exists, okay, in two-player zero-sum game. Okay, any questions so far? Okay, so Neil, what time are we breaking for lunch? Okay, no problem. So maybe I can finish the first part and then second part we can do after lunch then. No, I have few more slides, okay, so maybe I'll skip this slide. There is a very interesting connections with Lagrange duality. I don't know if some people, how many of you have looked into a Lagrange duality actually? This weak duality theorem, strong duality theorem, okay, very few. See, essentially in optimization literature, when you go to the convex optimizations and nonlinear optimization, I'll just gloss over it, I will not go into the detail. There are two very important results called weak duality theorem and the strong duality theorem. So this weak duality theorem and strong duality theorem are essentially what we saw just now. What we saw, that min-max is greater than or equal to max-min. That in optimization literature it is called a weak duality theorem, okay? And what we saw, that if min-max is equal to max-min, that is what they call duality gap is 0, and in that case saddle point exists. That is called strong duality theorem in optimization literature, okay? So maybe I'll stop till here. I mean, in Lagrangian duality I am saying there are several duality, Fenchel duality, this duality, that duality, but Lagrangian duality is one of the important type of duality which we study in optimization literature, and where these are the two cornerstone actually, weak duality theorem and strong duality theorem. So they are essentially this theorem, right? Maybe in future if you encounter, recall this talk that time and you will be able to connect them easily. Okay, so then the question now becomes is that you may ask that, okay, even if the saddle point doesn't exist, ditch it. You told me that at least min-max will always exist, right? So how the hell I compute min-max? Because I know guaranteed min-max will exist always, may what come. Saddle point may exist, may not exist. But min-max and max-min will always exist for any function. So let's worry about computing them. How do I compute them? For the table formulation it was easy, you take the row min and column max, or column min and row max, and all that was very straightforward, right? But if it is a very general arbitrary function, how do you compute them? So again, the problem is not easy, but of course it is not as hard as computing the saddle point if they exist. So there are some results, maybe I will not go into the detail. There is a famous theorem called Denskin theorem actually, those who are interested can look into it. That Denskin's theorem talk about certain conditions, that if you have certain property about the function, like the domain is in Rn, y domain is compact in Rm, and f of x is C0 plus directionally differentiable, and when you claim the y in x, it should be C0. C0 means it's a continuous function and it should be convex. In that case, it tells you that how can you get the gradient of phi of x, because if you have to compute min-max, what you need, as long as you have good handle on function phi of x, you can find the minimum of phi of x, you are good to go, right? So, and how can you find the minimum of phi of x? As long as somebody can give you gradient, because if you know the gradient, you keep doing the gradient descent actually, right? Move some step in negative gradient direction, then go some distance, again compute the gradient of the function, go in negative gradient direction, because negative gradient direction is the where the function value decreases always, right, actually. So keep going in negative gradient direction. So if somebody can give you the gradient of phi of x, you are ready to apply. I mean, you are ready to apply the standard gradient descent algorithm. But the major challenge in this problem comes, where do I get the gradient of phi of x? That's little non-trivial. So what happens is under this condition, he gives you the gradient, that this could be the gradient, and which is easy to compute. But this may not be always the case. There is another results in economics people talk, there is this thing called envelope theorem. So there again this maximization could be done. Let me not go into all of them. So there are like that, there are several such very peculiar specific cases, right? If this and this is satisfied in function, go this way. If this and this is satisfied in function, go this way, right? So there is a hell lot of literature actually. I just wanted to allude some of these terms in your mind, so that at any point in time, should you require to compute min-max point, you can look into some of this literature, right? Beyond that, I think it is out of the scope of this talk. All right, so I think this logically completes my first part. It took longer than what I was expecting, but I feel that it was worth it, I hope so. And this second part, which is more of CS part, I will start with, I'm thinking maybe we can start with CS, but let me stop by flashing one slide on this CS part. Maybe I'll resume that. What will I talk after the lunch? Let me first tell you that. And why this connection? So, can you see that these images, right? In this picture, these images, but for the last column, all the images are handwritten digit by some human being. They were scanned and taken. Some human being sat down, like how you write the numbers, right? So some handwritten digits, images, but for the last column. Now what is the last column? Last column is computer generated image, right? And they look almost real. I mean, they look as if some human had written it down. But no, computer was trained on these images, right? This deep learning algorithm, which I am going to talk about, this is GAN model. And then computer was shown all these images written by human. And then after a while, machine was capable of producing at its own new images. And they are not just replica. Can you see that they don't sound like as if they are just copying and pasting some previous image. It sounds a new variation, as if some new human being has written the digit 9, right? Similarly, these are the images of bedroom. Actually, these are the images generated by computer just out of the air. Possibly such image may not ever exist in this whole universe, right? What was computer done? Computer was exposed lots of bedroom kind of images. So it's a real picture of several scenes of bedroom, like this kind of things. Shots were taken, and those large number of images were given to this algorithm called GAN. Then after a while, when the algorithm learned enough pattern in those images, then it starts generating at its own new images randomly, right? Think of that as an artist actually, right? Think of this as a kid whom you show 100 images and ask the kid to use their imagination and draw 100 plus 1th image, which look very similar in this theme actually, theme based images. Computer today, in today's time, they are capable of doing these kind of things actually, right? And what is at the core of it? The core of it lies all these concepts which I talked about. The min-max point, the max-min point, the saddle point, and we will see this connection after the talk actually. That how computers are made to generate these images, which sounds almost like a miracle actually, right? But it's all maths at the end of the day. If you know good amount of fundamentals, it's all that solving that optimization problem, trust me. And you know, these images may be looking blurred. And the culprit of this blurredness is what? That optimization problem which I showed you, the algorithm is not able to solve it to the optimality. If you invent a better optimization algorithm, trust me, you can improve the quality of these images. The game is as simple as this. But that's the hardest part, designing the right optimization algorithm. So if you know the optimization really good, trust me, you can do wonder actually. Like you can come up with these kind of crazy things actually. Okay.